The state of Hawaii has committed to generating 100% of energy from renewable sources by the year 2045. In 2016, the Hawaiian Electric Company (HECO) and the National Renewable Energy Laboratory (NREL) generated a set of computer models that estimated possible pathways to achieving this goal. Each pathway or scenario of the PSIP or Power Supply Improvement Plan achieves the 2045 goal through a different set of renewable energy sources such as utility-scale solar, terrestrial and offshore wind, and biofuels. The PSIP plan was highly detailed. HECO published the plan as a series of 4 books, each one hundreds of pages long and filled with detailed charts, dense technical writing, and countless data tables. Even for energy experts, these books were challenging to digest. The Hawaii Advanced Energy Nexus, or HAVEN, began as a collaboration between the Hawaii State Energy Office and the University of Hawaii at Manoa Computer Science Laboratory, LAVA, the Laboratory for Advanced Visualizations and Applications. The first iteration of HAVEN was a chart sandbox where users could access the data at the heart of the PSIP plan and easily and rapidly generate charts to compare the different scenarios. The chart sandbox was a resounding success, but even so, the Hawaii State Energy Office realized the importance of sharing the state's plans with the general public. As such, the HAVEN Projectable project was born. During the planning phase, the following goals were established. 1. Visualize the complex data in a way that individuals without relevant background knowledge could easily and instantly recognize and understand the cost-benefit trade-offs of the various pathways, as well as gain a deeper understanding of the land-use conflicts that could arise. 2. Present the data in a surprising way to capture the attention of people who may have otherwise held little interest in the topic. If these goals were achieved, the HAVEN Projectable would stimulate topical discussion and deepen the intuition of people who, before they saw the visualization tool, had few or no opinions on the problems at hand. The idea behind the project is simple. Create visualizations showing the amount of land required to achieve the goals set forth by the various scenarios in the PSIP plan. A scenario that requires large amounts of solar will have a larger footprint than one that is heavy in biofuel or offshore wind. The HAVEN Projectable uses a physical structure, a type of data sculpture, as the foundation for the visualization tool. This physical artifact can encode data relevant to the project's goals. While topographical data can be expressed using contour lines, not everyone is familiar with the technique, and even then, it takes considerable effort to understand the terrain using only these lines. Instead, we used a model of the island of Oahu, cut from foam with a CNC machine, and later Hawaii Island, Maui, and Puerto Rico as the base, and projected our data directly onto the artifact. Using this projection mapping technique, we were able to present terrain information to the users in a way that could be instantly and completely understood. Since the table was intended as a public outreach tool, it needed to be portable and run without internet access. We chose an Alienware 15RP laptop running Windows 10 to drive the application. The physical table is built with 80/20 aluminum, chosen for its lightweight, sturdiness, and durability. A ViewSonic 4K projector is mounted on the crossbar above the table. The table stands at 70 centimeters and is divided into 2 sections. On the left side, the interaction zone is 30 centimeters long. In this section, 3D printed tangibles with augmented reality markers are placed onto a piece of frosted translucent acrylic, and 2 720p Logitech web cameras track the markers from below. On the right is the 90 centimeter long data zone. The island is placed onto the black acrylic in the center of the zone. Black was chosen for its ability to show sharp, crisp colors. The software is written in TypeScript using Angular 2 and Node.js. Angular was chosen because its strengths are real-time updates and data handling. The layers and charts were created using D3. The augmented reality portion of the application was implemented using the Aruco.js library. Aruco.js is a lightweight, open-source library that is built on top of OpenCV. Aruco was originally developed by Rafael Munoz and Sergio Garrido in 2014. And the markers have a black border and an inner matrix that is a unique mixture of white and black squares that identifies the ID of the marker. The strength of this technique is that detector object returns the position of the 4 corners of the marker, which can be used for tracking, as well as to calculate the rotation of the marker as the corners change position relative to one another over time. HAVEN Projectable's markers are 3D printed with black PLA filament and placed underneath the 3D printed tangibles, called pucks. In early iterations of the pucks, we used opaque plastic cylinders with small flashlights inserted to aid in camera tracking, but this technique was problematic as the flashlights had limited battery life and their output faded as the battery died, which would unexpectedly cause poor tracking. Ultimately, the pucks were created with a simple and effective design. They are small, thinly walled cylinders printed with translucent PLA. Their translucence allows the light from the projector to shine through the puck, even in an otherwise dark room, creating a clear silhouette on the surface of the interaction area for the cameras to track. The projectable software follows the observer design pattern. Events and state changes that occur within specific components are handled by a central service and emitted to all subscribed components for real-time updating. The publish subscribe implementation was done through the RxJS library. This design pattern allows for simplistic code, allowing for components to remain entirely independent of one another and from the data itself. Input data comes through two web cameras. This data is fed through a video feed component, where thresholding is applied to convert the images to black and white for improved Aruco marker detection. The Aruco.js detector identifies the markers by ID number, and the Haven projectable system stores the location of the four corners of the marker in the projectable marker class object, one for each marker, year, layer, add remove, and select scenario. The projectable marker class will evaluate the data, and if a rotation is detected, the planned service will be notified to call the correct function, depending on the direction of the rotation. The HTML that is displayed is controlled by various components, each with a specific job, such as controlling the pie chart or the map legend. Any changes in the state of the system are broadcast by the planned service to all appropriate subscribers, who then update the components that feed into the map main component, which consolidates all HTML cohesively. All settings for a specific map, such as Oahu or Maui, are stored in a single file, called the plan. This file stores everything from the GPS bounds of the map, custom CSS values, and data file paths, to the implementation of the layers. With this design choice, it is easy to set up new geolocations by copying the plan file and changing relevant fields. The Haven projectable uses two types of layers. The first is static layers. The static layers encode information that does not change over time, such as agricultural zones and government lands, as future changes have not been modeled. The second, and more interesting, layer type is dynamic layers. These layers, such as solar, wind, and distributed energy resources, change with time. NREL's models identify the areas of land that are most suitable for solar energy generation, based on characteristics such as consistent sunlight and slope. Our layers divide these areas into 5-acre segments, shown as a white grid, drawn with D3. As the user proceeds forward in time, by rotating the year puck, the white grid segments are filled in with orange, showing the amount of land necessary to generate the amount of energy specified by the selected PSIP scenario. Our algorithm fills squares by the highest capacity rating first to ensure the smallest possible footprint. All UI elements are projected directly onto the pucks and are generated with custom CSS and TypeScript using the transform function and keystone-based animations. This projection is possible by first calibrating the pucks by placing the puck into 6 specified locations on the interaction zone. The specified locations are generated by the application, and their XY coordinates are in the screen coordinates. When the user places the puck into this location, the camera is detected, and the application creates a mapping between the screen and camera coordinates. The response to the Haven projectable has been resoundingly positive. A student project at the University of Hawaii at Hilo adapted the Haven projectable, and their product is on display at the Imaloa Astronomy Center in Hilo, Hawaii. The projectable has been featured locally by multiple news outlets. The table has been displayed at renewable energy conferences in Washington, D.C., Ohio, and Maui. A news article from University of Hawaii News wrote, an interactive 3D projection mapped model of Oahu, developed by University of Hawaii at Manoa students, showing layers of data for the state's plan to run on 100% renewable energy by 2045, generated lots of buzz at a national energy conference in February in Washington, D.C. As the contribution for the state of Hawaii to the event, the table was operated by the Hawaii State Energy Office. The article wrote, a dozen or more states were interested in adopting the technology, said Chris Yunker, Energy Systems and Planning Branch Manager for the Hawaii State Energy Office. Assistant Secretary of the Office of Electricity Bruce Walker had come by, and he showed interest for the Department of Energy to adopt the technology itself. Interest in the Haven Projectable led to the creation of a second version, Haven Projectable 2.0. The data zone is 2 times larger and uses a touch-screen interface instead of the tangibles. The Haven Projectable 2.0 was the centerpiece of the Illumination Hawaii event in Honolulu in March 2022. It has been an honor to contribute to Hawaii's sustainable future.